Okay, good afternoon, everyone. If you're in Europe, or good night if you're in Asia, good morning if you're in America. So welcome to today's web presentation by Rosa Bulow. Worked for a long time here in the corridor where SCM is located. And now she's moved recently to the Universiteit of Utrecht, and she will give a hands-on demonstration of how to use the FlexMD code that she and others developed that can be plugged into ADF and other modules, as well as external codes for running advanced QMMM type calculations, advanced molecular dynamic type calculations, and in particular adaptive QMMM. So with that, without further ado, I'd like to hand over to Rosa. And Rosa has agreed to take questions via the chat function afterwards. So if you have any questions, you save them up until the end of the presentation. You can always afterwards email questions as well. Okay, so I'll switch over to Rosa now.
Hi, Vader. Hi, everyone. Okay, I assume that you can all see me now. Welcome. And Vader, thank you for your introduction. As Vader said, I'm going to talk about FlexMD, which is, okay, there it is, which is a code that I developed. It's actually a Python library and a wrapper around the ADF suite that allows you in the first place to do molecular dynamics with all the programs inside the ADF suite, but it was particularly developed to do advanced types of QMMM simulations, QMMM molecular dynamics. I decided to put a picture of myself here because I found it so strange to be just a voice, so there I am. Okay, I still have to figure out how to turn the page now. There we are. Okay, so as you all know, the ADF suite of programs contains a set of separate programs. Many of them are quantum mechanical programs, ADF for all the DFT, density functional theory, BAND for the periodic DFT, DFTB if you want to be faster, it's a semi-empirical approach, and then ADF also ships MOPAC, which contains a lot of semi-empirical functionals like PM6, PM7, also for doing fast quantum mechanical calculations. And then there are also classical force field molecular mechanical programs inside the ADF suite, such as ReXFF developed by Adrie van Duin and UFF, the Universal Force Field. And some of these programs, they already give you the possibility to do molecular dynamics, but these are specific implementations. So they are, for example, for DFTB, ReXFF, and UFF, 3 different implementations of molecular dynamics. So what FlexMD offers as a Python wrapper around this suite is a unified way to do molecular dynamics with these programs. This is depicted here schematically. So first of all, FlexMD exists as a unified way to do molecular dynamics on the potential energy surfaces provided by ADF, BAND, DFTB, MOPAC, ReXFF, and UFF. And we do this through an interface with ACE. So that's an external Python code, atomistic simulation environment. So that's one, molecular dynamics. The second thing that FlexMD has been developed for is to do QMMM. So it provides you a way to do flexible combinations of all of these programs that you see above in QMMM simulations. So for example, if you have a very large molecular system, which is schematically depicted by the rectangle that you see in this picture, then you can imagine that you might want to treat only a part of that system. There's only a local part of that system that you're really interested in, and you might want to treat only a small part of that system and the atoms in there using density functional theory, while the rest of the system you prefer to treat using a classical force field. Okay, so ADF for a small subset of atoms inside a region and UFF for the rest. Well, that is something that FlexMD can do. So this is an example of QMMM, but we can easily also make other combinations, QMQM, MMMM, and even multi-layer combinations. So here's a schematic description of such a multi-layer combination where on the one hand you can, for example, take a small region that you treat with DFT, then you take a larger region around it that you treat with DFTB, which is a bit faster, and the rest of the system you treat with a force field like UFF. And it's also possible to define another specific region and treat that with, yet again, a different method like ReXFF. So this is very flexible. And we do all this all just within the ONIUM framework, which means that it's all mechanical embedding. So at this moment we don't have electrostatic embedding implemented, meaning that the partial charges of the MM atoms are not included in the QM Hamiltonians at this moment. Okay, now traditionally it's common practice in QMMM to have the QMMM boundary cut through covalent bonds, as is schematically depicted here by these two C atoms with a bond that lie across the boundary. Why is this? This is because QMMM was originally developed really for very large molecules like proteins, where you want to treat a subregion within a molecule, QM, and the rest of the molecule, MM, which means that you have to cut through covalent bonds. Now FlexMD is able to do that, but it was actually originally developed for this situation to study in a QMMM manner solid molecules, a solid molecule in or a set of QM molecules in an environment of MM molecules. So this is really a particular case of solution systems. So we have the possibility to cut through covalent bonds, meaning that we have link atoms implemented, but this came into the code later, and well, the use of that is a bit more complex, so I will not go too deep into that today. Okay, so like I said, this code was developed for QMMM in solution, and doing QMMM simulations in solution, if you want to do that well, that has its own challenges, which I will discuss in the following few slides. Okay, I will discuss it using this example. This is an example solute molecule. It's dihydroxyacetone, and this is a schematic representation of that same molecule. And well, I want to do a QMMM modeling of that molecule in water. So here you see dihydroxyacetone solvated into a whole bunch of water molecules. Now I can do easily a QMMM simulation on this system if I treat only the solute molecule QM and all the water molecules around it using a classical force field. That is easy and fairly straightforward. But in many cases, I might want to include, so the region I'm interested in is the solute molecule itself, but I might want to describe very well also the water molecules that are directly interacting with the solute molecule, because there might be charge transfer going on, there might even be proton transfer going on. So this can be very desirable, and if I do that, I run into problems. QMMM like this is not so easy, and QMMM like this is actually not QMMM as it's usually done, because the original QMMM, the one that received the Nobel Prize in 2013, was really focused on biological systems, and they are actually quite special systems in that the active site, the part of the system that you'd want to treat, QM, is fairly well shielded from solvent molecules, which means that if you define a set of atoms at the beginning of your simulation as QM, you'll see that many picoseconds later, or probably picoseconds, those atoms will not have moved very far away from their original positions. Whereas if you do the same in a diffusive situation, like in a solution, so the example on the left, you'll see already after a few picoseconds, you'll see this happening. So the water molecules that we had defined as QM have diffused very quickly far away from our region of interest. So this diffusivity problem is the thing that, well, that I'm working, that I'm trying to solve, and I'm developing methods for that. So a method that me and several other people throughout the world are focusing on is adaptive QMMM, where we do, I guess, the intuitive thing. We first, at the beginning of the simulation, we define a sphere around our solute molecule. All the water molecules inside the sphere are treated QM, and all the water molecules outside the sphere are treated MM. And then when a water molecule, like the one with the arrow on the left, is about to exit the sphere, that means the next time step, it will be treated MM. So we just change the description on the fly from one time step to the next. Now this is very straightforward and it's easy to implement, but if you do it like that, from one time step to the next, you'll get very strong jumps, changes in the energy and changes in the forces, and this will result in a severe heating of the system that starts at the QMMM boundary. And if you use a normal global thermostat, you'll see that at the boundary the system really heats up. Okay, so what we try to do is we try to prevent this heating. And we do this by introducing a second sphere so that the region between the two spheres is the buffer zone. And all the water molecules in the buffer zone between the two spheres, they are gradually changing their character from QM to MM and vice versa. So this is how that works in practice. So on the left-hand side you have a representation of our solute molecule in a two-dimensional situation, and on the right-hand side you see the same thing in a one-dimensional depiction. So we have the dihydroxyacetone and a water molecule sitting in the QM region. So this, by the way, is the example situation where we have only one water molecule inside the buffer zone. That's the simplest situation and the easiest to understand. So we have that one water molecule inside the buffer zone, it's the green one, and then we have a bunch of water molecules in the MM region. What we do now is we do two calculations, one where we treat, that is calculation A, one where we treat the green water molecule QM, and one where we treat the green water molecule MM. And now our final, so we extract the gradients or the forces from these two QMMM calculations, and our final force that we use in our molecular dynamics propagation of the system is a weighted average of these two forces, of these two sets of forces. And the weights, WA and WB in the equation on the bottom, this weight is defined by where the green water molecule is in the buffer zone. Okay, so let's go to the slightly more complex situation where we have two water molecules inside the buffer zone, so two green water molecules. Because we have to account for the fact that these two water molecules have different QM character, we have to do three calculations now. Two is no longer enough. So the first calculation treats those two water molecules MM. The second calculation treats only one of those water molecules QM, and as you might expect, is the one that is closest to the QM region, so has the most QM character. And the final calculation is the one that treats the QMMM calculation that treats both water molecules QM. And then the forces, the set of forces that we apply to our whole system is a weighted average of FA, FB, and FC. And the weights are now defined by the positions of both the water molecules inside the buffer zone. So that's what we do. That's how adaptive QMMM works in practice. And now I will go on to demonstrate some of the main features of FlexMD, how to use it. And I'll do this in 3 steps. First, I will demonstrate how to do molecular dynamics, which we can do in the same way using ADF, BAND-D, FTB, MOPAC, or ReXFF, or UFF, but I will demonstrate this only for ADF. I will spend most of my time on this demonstration because when I move on, after this I will move on to demonstrating how to do a QMMM molecular dynamics simulation for a solution. And finally, I will explain how to do an adaptive QMMM simulation. But then, since you already have an idea about how FlexMD works, I can go through steps 2 and 3 relatively quickly. So let's move on to that demonstration. Okay, I'm just going to click this away. The first thing we're going to do for a normal molecular dynamics simulation is to draw a water molecule, because we're going to do this molecular dynamics run on a water molecule. I'm just going to use the ADF input GUI for that, and I assume that all of you have some experience with this, and even if not, you see it's very, very simple. I've now drawn a water molecule, just going to save the coordinate somewhere. It was already there. Okay, I'm going to overwrite it, save the coordinates. There we go. Right. So here we have the coordinates. I'm just going to show you that they are indeed the coordinates, the XYZ coordinates of a water molecule. Now I'm going to get you an input file for a molecular dynamics simulation with FlexMD. There's an example in the ADF example directory, which I'm going to use as the start. So I'm going to copy that here. The directory is ADF home/examples/semlib. And the example that I need is this one. So I seem to have typed it correctly. Let me open this example input file. It looks like this. Okay, there's some information in this example input file that you won't need when you want to run regular molecular dynamics simulations, and that's mainly everything that comes after the job.run command here, because that's cleanup. It throws away files, and we don't want any files to be thrown away. So I'm going to remove that. Okay, and then you see that that a FlexMD input file for running a molecular dynamics simulation of water with ADF is really, really very simple. So these are the examples as they are inside the ADF directory. So for what we want to do, we might want to make a few small changes. For example, the coordinate file that I've stored is not a PDB file, but it's an XYZ file, so I need to change the name to the proper one. Okay, so here are the steps that I take to run a molecular dynamics simulation with FlexMD. First, I define. I'm assuming that everyone has some basic knowledge of Python, so I won't spend too much time on that. The first thing I do is I define a molecule object which contains the coordinates, and it's called MD molecule. Then I create an ADF force job calculation. What it does, it's the thing that is able to compute the ADF energies and the ADF forces, and I give this my molecule object. So now I'm able to compute ADF energies and ADF forces. So then I pass this, then I create an ACE-MD propagator job. This is the thing that can do MD, and I give it the force job. Now the ACE-MD propagator job doesn't ask questions about where the forces and energies come from. It just uses them to do molecular dynamics. And then I can change some settings for the ACE-MD propagator job. For example, here I've chosen to use a thermostat. And I've set the time step to, the thermostat by the way is a Rosa Hoover thermostat, that's default, and I use a time step of 0.5 femtoseconds. So femtoseconds is the default, the unit, the internal unit of FlexMD. Okay, so now I'm almost done with my input. I now create an MD manager object which controls all the input and output for FlexMD, and I pass it the MD job. With that, I can start running my molecular dynamics. You can see here that I'm only doing 2 steps. I might want to do a few more here. Let's do 5 steps because I also don't want to spend too much time waiting for the output. But of course I can do 5,000, 50,000, 500,000 if I want. Okay, so this is, with this I can run a perfectly nice ADF molecular dynamics job. But as you can imagine, there are a lot of default values set here that you can see and I didn't specify. For example, what kind of ADF functional is used? Well, the default functional is BP86, but you can set whatever you want in the following way. PBE, whatever you want. I'll give you just one other example. You can set the basis set to be TZP, and there are many more settings you can set, and you can change for the ADF calculation. I just want to show you how you can find out what the possible settings are, and I'm going to do that using the Python user interface. So there we are. I'm using Start Python, which is the Python the Python program is distributed by ADF. So there we are. So it should have already FlexMD in there. So what we're going to do now is import the ADF force job. That worked. Now we're going to create an ADF force job. Now we're going to use the help function of the interactive user interface to see what kind of settings there are. So here you can see all the possible settings. There is set basis here. There are many, many more. You can a useful one would be Zora, Convergence, Cosmo, DS. Well, you can see for yourself. Okay, so let's return to our input file. And now you know how to set all the settings for the ADF force job. You might also want to set, be able to set the temperature for your molecular dynamics. This is a very basic setting, and of course you can see what kind of settings the FlexMD propagator job has using the same help function of Python. But I'll just show you how to set the temperature. I've set the temperature to 300 Kelvin, which is actually also the default value. Now we are ready to run. We have an input file, so let's do it. This input file automatically runs start Python, which imports FlexMD, so all I have to do is run this data script. This didn't work, okay. Yeah, this is the reason. There we go. So you just have to run for 5 time steps. It means 5 single point calculations of ADF with some overhead because it's starting up ADF each time step. But it's not that slow. So let's see the calculation, the MD calculation of 5 steps is finished. Let's see what we have. FlexMD has now created 2 directories. One of the directories is ADF, which contains the information on, it contains ADF input and outputs, and the other directory is QMMD. Let's first look into the ADF directory. These are the files inside the ADF directory. The most important file actually is this one. It's ADF output something.out, because it contains all the output file of each ADF calculation. So this can grow very big very quickly. But the reason we're looking at it now is just to show what settings we have used. And indeed, as we thought, you can see here that we have used BP86, and you can see here that we've used TZP base set. So we have actually run the calculation the way we wanted to. So let's now, I'm sure you've all seen ADF output files already, so that's not the most interesting thing in the world. Let's focus on FlexMD specific files. The molecular dynamic files, they are in the QMMD directory. So here we are inside the QMMD directory. The most important files here are, first of all, I would say the energy file. So the file called energy00.dot. It contains the potential energy at each time step, the kinetic energy at each time step, and the temperature. So here it is. And the unit, as is the internal unit of FlexMD, is kcal per mole. So here we have the energy information. Then the file traject00.dcd is a file that contains the coordinates at each time step of the entire system. Now this is a binary file and contains only the coordinates. So if we want to visualize this in some way, we need to tell our visualization software where the elements are. And the information about the elements is in the file coord.psf. So I'm just opening it because that's a text file. The most important thing in this file is that it tells you that the first atom is an oxygen, the second atom is a hydrogen, and the third atom is a hydrogen again. It contains a lot more information, like where the bonds are and where the angles are. But in this particular calculation, that's not used. Okay. Of course, we can use these 2 files to visualize the trajectory using, for example, my favorite visualization software, VMD. That would work in this manner, but I'm not going to do that in this case. you see a trajectory of a water molecule, 5 steps. Another way to look at the trajectory is to use FlexMD. So we can use the analysis tools of FlexMD to get information about the trajectory from the trajectory file. I'm going to write an example script that gives you the OH bond length at each time step. This is it. This is a PDB molecule object. This is like MD molecule that I've shown before. It's a FlexMD molecule object. It contains the elements and it can contain coordinates. And this is an object that contains information from a DCD file. Okay. Let's first create a PDB molecule object. You can use the file that we created with ADF input. And then let's create a DCD object. Now we're going to run over the snapshots inside the trajectory. Let's use a big number. And we're going to read what's in the DCD file. Coordinates and information about the periodicity, which in this case isn't there. Let's read frame I, and let's put the information from frame I into our PDB object. Now, because we don't have 1,000 steps but only 5, we should make sure that this loop ends when there are no coordinates in the DCD file anymore. So let's say if coord equals none, break. Okay, so now let's get these OH distances for each step. Let's just call it this. Get bond length is a method in the PDB molecule class, and we want the bond length between atoms 1 and 2. So that's the oxygen atom and the first hydrogen atom. Now let's create an output file to which we're going to write this information. And in that file we're going to write the step as well as the bond length that we've just created. Okay, for the moment this looks reasonable to me. Let's use this script. Okay, it was almost correct. I should have imported scm.flexmd. There we go. So let's see what we have created. We have created a file called ohbond.dat, which contains, for these 5 steps, the OH distance. Of course, we can do many, many things. And you can, of course, use again the help function of the Python interactive interpreter to find out all the methods, all the analysis methods inside the PDB molecule object. There are many. Is there something else that I should tell you about this, about the files in this directory? Yes, there are 2 more important files here. The first one is QMMD00.res.val. This contains the velocities at the very last time step. And there's the one that ends in .coor. This contains the coordinates at the very last time step. So these files are a pair, and they can be used to restart our our MD run. So let's go one directory up. if we run a script like adf_h2o.py in a directory that contains a QMMD directory, and if inside that QMMD directory is such a pair of files, .core and .vel, then the script will try to restart automatically from that pair of coordinate and velocity files. So that's automatic restart. Besides automatic restart, there's also a way, because the coord and the vel files, they are binary files, and there's a way to read these binary files directly and use, for example, the velocities in the .vel file at the start of an MD simulation. So I'm quickly going to show how that is done. This is the function that needs to be imported. Read binary coordinates. And let's say I'm going to read these binary coordinates here, and I'm going to read them into a list called vels. Okay, so that I have done that here. And then I can use these velocities to start an MD simulation from in the following way. So this is again, I would say, fairly straightforward. Okay, I'm not going to do this. This was just a demonstration of the restart possibilities that we have. So this was all I wanted to say about how to run a regular MD simulation with FlexMD. And now I want to move on to how to do a QMMM simulation with FlexMD. So let's go to the directory QMMM, and let's draw now two water molecules and do a QMMM simulation where we treat one of the two water molecules QM and the other of the two water molecules MM. So it has to be dimer. So let's see if I can make something that behaves like a water dimer. No. Okay, but let's optimize this for a moment and see if it goes to a more reasonable structure. Okay, it's good enough for me. Let's save these coordinates. Okay, I hope this worked. But of course the file is there. Okay, so to run a QMMM simulation, we should again copy an example from the examples directory in the ADF home and start with that. Now this one has a more complicated name than the previous one, this example. So this is a QMMM run that treats one of the water molecules with DFTB and the other water molecule with UFF, so it should be fairly fast. So let's copy this thing here. It seems to have worked, so I typed correctly. And there we are. So this input file is a little bit more complex, but again, as before, everything that comes after job.run we can remove because it was just cleanup. Again, a molecule object, an MD molecule object has been created. So we have to read in the correct coordinate file. We use that molecule object to create a DFTB force job in this case, and we put some settings here, like we want to set dispersion. Then we create another molecule object. We create a molecule object again. We have to do that. And we use it to create our force job. So now we have a QM force job and an MM force job. We combine them to make a QMMM force job. So the QMMM force job is created by passing both the QM job and the MM job and one of the two molecules. And we specify which of the atoms we want to treat QM. And in this case, numbering starts at 0. Okay, so we want to treat atom 0, 1, and 2. That's the first water molecule quantum mechanically, so with DFTB. So now we've created our force job, and as before, we can just use that force job to create an ACE-MD propagator job, set the same settings as before. We pass the ACE-MD propagator job to the MD manager. In this case, I gave the MD manager this force job as well, but that's actually not necessary. I could remove it. It works, but it works as well, but I could remove it. Okay, so one important thing that I need to say about this, I've told you that FlexMD has been developed to do QMMM, where you don't cut through covalent bonds. So separate molecules are treated QM and separate molecules are treated MM. As a result, FlexMD finds out where the bonds are, and if I give FlexMD a set of atoms to treat QM, it's going to test what the molecule is that atom belongs to, and it's going to treat that entire molecule QM. So here I passed all 3 atoms in the water molecules to QM region. Now things would be exactly the same if I would only pass atom 0 and do my QMMM calculation that way. Okay, so as I told you before, it is possible to cut through covalent bonds, but this was a later implementation and it's more complex, and I will not discuss that here. Okay, so this is basically an input example for a QMMM run. Let's save it and let's run. Again for 5 steps, and then look at what output files have been created and discuss those. Again, through the 2 directories that have been created, sorry. One of them is the QMMD directory, which is exactly the same as the QMMD directory we saw before. It contains only the molecular dynamics results, and it looks like this. So that one looks exactly the same as before, and we don't need to discuss it again. The second directory is this directory called QMMM forces. Let's look what's in there. The most important thing that is in there is the directory QMJob and the directory MMJob. And if we go into the directory QMJob, you'll see that it contains input files and output files for the DFTB calculation. Let's look at an example input file. And you can see that in fact, even though our total system is 2 water molecules, the DFTB calculation was performed on only one of those. You can also look into the MMJob directory, and this has the input and output files for the UFF calculation. Actually, I want to look at an input file. Let's look at the example input. You can see that in this, so there are actually 2 MM jobs computed in the QMMM calculation, one that treats a small system and one that treats the big system. This input file is for only one of the water molecules. Okay, so everything works the way we want it. And I think that this is actually enough. With this, it should be clear how to run a regular QMMM calculation using FlexMD. So let's move on in complexity level, and let's go look at adaptive QMMM. In this case, I'm going to draw a little more complex system because adaptive QMMM is specifically designed for solutions, so I need to create a solution. So let's first remove these 2 water molecules and create an XYZ file for methane in water. So here's a methane molecule. Now I would prefer to, it's a solution, so it needs to be finally a periodic calculation. So let's make a periodic representation of methane Of course, ADF is not a periodic program, so in order to be able to do that, I need to go to a different code, like DFTB. There we are. Okay, this is in fact exactly the lattice size I want. I want something fixed with 15 angstrom, but I have to tell the system, I have to tell the GUI that I want to create a bulk system. So with lattice vectors in all 3 directions. So now I want to dissolve this. So let's open the builder to put some water around this methane. Okay, I've done this before, so clearly everything is already here. I would like to fill a box with 110 copies of water around our methane atom. And this will give me a final density that is very reasonable for what we want. So let's generate this water box, or this solution. There we are. We have methane in water, and it looks fairly like we would expect. So I'm going to export these coordinates. There we are. Okay. So again, I need to copy a script from the example directory to start my adaptive QMMM simulation here. ADF home /examples/SEMlib. This is where all the FlexMD examples are, and the one that I want now is called QMMM _mopac SEM UFF _H2O. And then I need to get the Python file that's in there. Let's hope I typed everything correctly. Yes. Okay, so now I have the input file here, and we're going to have to adjust it again a little bit to do an adaptive QMMM simulation for this particular system. There we are. Again, everything that comes after job.run we can remove, so that makes the input file a lot more simple. Okay, we don't want, so here we create our molecule object, and we need to, of course, read the correct molecule XYZ file, which is called, sorry. There we go. This is the name of that XYZ file. Now, this is a periodic system, and FlexMD is not able to read the periodicity from an XYZ file, so we have to tell FlexMD what the periodicity is. We do it in the following way. Too many M's. Set box. We give it a list with the diameter of the box in all directions. And then we use this molecule object to create a MOPAC force job. And now, and then the QM job is created, and now we have to start creating the MM job. Again. And we have to pass the periodicicator. Okay, I'm going to type it. Okay, and then we create the MM job. We put them together in a QMMM job, and this time we don't have to say anything about which atoms are QM and which atoms are MM, because that is going to be decided in the adaptive QMMM part, which is which is going to contain this QMMM force job. Okay, so the adaptive part is in these 3 lines. The first object we create is the one that controls the size of the QM region. So I've shown you before in my introductory slides that in adaptive QMMM you have three regions basically. There's the active region where everything is treated QM. Then there's the buffer zone where the molecules change their description from QM to MM and vice versa in a continuous way. And then there's the MM region. So of course it means there are two boundaries, and here in the variable borders contains these two boundaries. The first one is at the radius of, in this case, 3 angstrom from the QM center, which we are going to define as the methane molecule or the methane carbon. Usually I take around 4 angstrom for this first radius, but I want my calculation to be, my simulation to be fast now, so I'm going to choose 3.2 for the inner radius. Usually I would take the width of the buffer zone about around 1 angstrom. Actually, usually I use 0.9, but no smaller. But for this particular example, again, I want to be fast, so I'm going to choose an outer boundary of 3.5 angstrom. Okay, so the next thing I'm going to do is I'm going to create this partitioning object, which defines actually how what this weighted average looks like. Okay, and here at the end you see method equals max x, and that's a particular type of weight function that I have developed with some co-developers, and it's called DAS. And there are other flavors of adaptive QMMM inside FlexMD as well, which you call with different keywords here. Okay, now I have to add, so there are a lot of default values here again, so I have to add a few things in here to be specific and actually to make it work right now. One of them is I have to define the center of the QM region as the carbon atom. So it goes with, happens in the partitioning object, and the keyword is, the argument is the center equals 1. So the first molecule in our coordinate file is going to be the center of the QM region. The second keyword I need to set to make this work is to explain the partitioning object what the adaptive molecules are. So the partitioning object is now going to recognize the adaptive molecules in the following manner. I'm going to define a variable called group center. So now all the atoms of element oxygen are the center of an adaptive molecule. So the position of the oxygen in an adaptive water molecule defines whether that water molecule is QM, MM, or something in between. Okay. Now, of course, I might not want to specify all the oxygens as adaptive, as the center of an adaptive molecule. In this case, I can get away with that because the only oxygens are in the water molecule. But I would like to, I might want to be more specific, and then I would have to define the following variable. Let me see. Let's say group center list, and then I can put atom numbers in, and I believe that they have to start at 1, but for this purpose I will leave them empty. And then instead of group center followed by an element name, I have to pass the argument there we are. So I hope this shows what I wanted to show. Then you can, so we could replace the group centers with group center nums, and then we have to provide a list of atom numbers. In this case, this is not necessary, so I'll remove this part of the code again. There we are. And there's one more thing that I need to define. here because then this partitioning object is used to create an adaptive QMMM job object. That's the final object that can create the adaptive QMMM forces. So I pass it my QMMM job as well as the prefactors or partitioning object that I've just created. And I need to specify one more thing, which is okay. If I don't do that, the total energy of the adaptive QMMM simulations will be shifted with some constant. That's the default, and I later decided that the default is kind of hard to understand, so please set in standard simulation zero energy to 0.0. Okay. So now we've created our adaptive QMMM job, and the rest is the same as all the other molecular dynamics jobs. We have now created a force job that we can use to create an ASMD propagator job, and that ASMD propagator job can then be used to create an MD manager, and then we can start to run. So here we run only 2 steps. So let's do that. And now the output of an adaptive QMMM job, okay. I see. Made this small error. And it needs to be. Okay. So now both molecule objects have the same periodicity, as they should. Let's run. Okay, so the output for an adaptive QMMM job is a bit more complex than the output for any of the other jobs that I've shown so far. It's almost finished, and let's see what the output shows. First of all, so this here is the first step. First of all, this is the QM region. This tells you that there are 2 oxygen atoms, so 2 water molecules inside the QM region, and these are the numbers inside the XYZ file of these oxygen atoms, so 74 and 185. There are also 2 water molecules inside the transition zone, which are these numbers, and then this line tells you something about where those water molecules, or the buffer zone, sorry. This line tells you about where those water molecules are inside the buffer zone. So you can see that both of these numbers are very high, 0.94 and 0.95, which means that both of them are very close to the MM boundary, so they have a very strong MM character. Okay, and then we do 3 separate QMMM calculations per time step. And this is and those are we call the partitionings, and this is the information about these 3 partitionings. The first partitioning treats none of the water molecules in the buffer zone QM, and this has a fairly high weight. So this is the weight of that partitioning, because we know that those 2 water molecules have a very high MM character. And this here is the energy of that partitioning. The second partitioning treats one of those water molecules, QM, the first one, 17, and the second one treats both of those water molecules, QM. So here are the weights, and here are the respective energies. So we do that for 3 steps, and then we were done. So again, 2 directories have been created. One is again that QMMD directory that we've seen before, and the other one is called add forces, for adaptive forces. And let's quickly look inside. The most important things inside the add forces directory are again QMJob and MMJob, which are the same directories as would be created during a QMMM, a normal QMMM simulation. Let's look at the QMJob. So here are MOPAC inputs and MOPAC outputs. Let's look at one of the input files. And you can see that it's actually well, a system with 4 water molecules. So all of the water molecules that are treated QM in the largest partitioning. And well, this is just a MOPAC input. This is the periodicity of that QM calculation for the last step. I should mention, let's go look at the input file again. I should mention that if you don't specify anything, then these three partitionings that need to be computed, or this set of partitioning that needs to be computed each time step, they are calculated in serial. Now you might want to, you might have a lot of processors available, so you might want to run them in parallel, and then you have to set the following keyword. In the adaptive QMMM force job, you say set parallel, and then you specify the number of processors that you have available. And if you do this, then your simulation, then all the partitionings will be run in parallel. Okay, so now I've shown you how to do normal molecular dynamics with FlexMD. I've shown you how to do QMMM with FlexMD in the case of a solution, and I've shown you how to do adaptive QMMM with FlexMD. I quickly want to spend one slide about further features that FlexMD has. I've already mentioned before that we can cut with our boundary through covalent bonds. So we have link atoms, but well, this is really complex to use. There is, however, an example in the examples directory, so you can find out how to do it. Then we have free energy methods like metadynamics and umbrella sampling with actually quite a lot of collective variables. Free energy methods, they are needed if you want to do molecular dynamics for a chemical reaction, for example, and you need to cross a barrier, which will never happen in a few picoseconds, so you need to speed things up a bit. For the adaptive QMMM part, we have many different flavors of adaptive QMMM. What I showed you with the keyword specified was a difference-based adaptive solvation developed by me. We also have sorted adaptive partitioning developed by Andreas Heiden. We have and Hai Lin. We have buffered force developed by Gabor Tani. We have flexible inner region ensemble separated, or FIRUS, which is a slightly different method, but it's also meant for QMMM in solution, and was developed by Benoit Roux. And finally, we have not only interfaces with the ADF programs, but also with a lot of other programs like NUMD, LUMS, CP2K, WASP, TurboMol, actually a few more. And we can do much more trajectory analysis than I've shown you so far. We can, for example, find hydrogen bond bridges, but we can also do radial distribution functions, we can do time correlation functions, we can do many things. Finally, I'd like to thank these co-developers of FlexMD, and of course you for staying with me all this time. I would like to get some questions, and I hope I can see them.
Yeah, okay, so thank you,
Do you have any
Rosa.
questions?
Yeah, so I suggest if people have questions, they can they can put them in the chat box, and they can also, of course, ask questions later via email. I just wanted to sort of advertise Rosa's overview paper, so I'll put that into the chat box now. So there's a link to the overview paper that describes all the different flavors for adaptive QMMM. And I guess, Rosa, that if you want to use all the different flavors, then the best way to see how to specify that is by using the helper function, right?
Yes. So you have different ways to call get partitioning object, and that should work.
Okay.
Yeah.
All right. So if there are any other questions at the moment, people can type them in the chat box now.
Mm-hmm.
Okay. Well, yeah.
Oh, you're welcome.
If not, at any rate, I will try to upload the video somewhere this weekend, and then people can look it back and, of course, pass it on to other people. And if then questions still arise, then Rosa will be available also via email. We can help you out with ADF-related issues. So yeah. Okay. So I see one
there's
question.
a question.
Yeah.
So the question is if we can look at the reactions in the QM region. Yes, we can. This is what the adaptive QMMM was developed for. I mean, I guess the question is, can we look at reactions with adaptive QMMM, right? And in fact, yes, we can. So the answer to that is simply yes.
And so do you have tools for tracking reactions? So can you, with all the...
So the main thing that you need to do if you want to look at reactions is to use a free energy method. If you want to look at the chemical reaction with molecular dynamics, you need to always use a free energy method. Probably you want to use umbrella sampling, or you'll want to use method dynamics, which are the ones that we have available. And then you can use these methods easily, I mean, very straightforwardly in combination with an adaptive QMMM force job. And so what you need to find is an example in the examples directory of, for example, method dynamics run, a method dynamics FlexMD input, and you can easily do that in combination with adaptive QMMM. So yes. And people have actually already done this, done chemical reactions with adaptive QMMM in the past.
Okay, great. Any other questions? Okay, let's assume that everybody is baffled by this very clear presentation, Rosa. So
of course.
I'll wrap up for now. Thank you again, Rosa, and thank you everybody for listening in. And
you're welcome.
See you next
and thank
time.
you for the invitation.
All right.